So now we're going to talk about exceptions and interrupts. So what are exceptions and interrupts? Well, an exception is a non-normal event that interrupts the normal flow of instructions. So it's something unexpected. Interrupts are external events that interrupt the normal flow of instructions. So these are something that's coming from outside the computer system usually. So examples of exceptions: divide by 0. You don't expect to have this happen, and when it does happen, it's going to interrupt what you're normally doing. How about a misaligned memory access? You're only supposed to make aligned memory accesses, so you don't expect to have misaligned ones. A page fault. So a page fault occurs when you try to access data that's not in the main memory, and the operating system needs to go get it for you. Or a memory protection violation. This is what happens when you try to access memory that you don't own the rights to, and this will cause your program to crash. Interrupts are external events, so for example a keyboard press. When I press a button on the keyboard, it's going to generate an interrupt which tells the computer to handle it. Or if the disk drive is ready with data, it's going to get an interrupt so the computer knows to go and get the data from the disk drive. Arrival of network packets are similar. So how do we handle these exceptions and interrupts? Well, when we get an exception or an interrupt, the processor is going to transfer control to the operating system, which is going to handle the event. So when the operating system is done, it's going to restart the program at the offending instruction. So that is, on an exception or interrupt, we're going to go to the operating system, and the operating system is going to take care of it. So let's take a look at a picture. Here's our program. It's going ahead and executing, and then we have an exception or an interrupt. When this happens, we stop executing our program and we go over to the operating system. Now the operating system is going to go ahead and execute, and it's going to process the exception or the interrupt by a special part of code called an interrupt or an exception handler. This handler code is going to take that exception or interrupt and figure out what to do about it. Then when it's done, we're going to return to the program, if we can, and the program will keep running. So it's important to remember here that while we go to the operating system and we come back to the program, there are some exceptions that are fatal. That when this exception happens, we can't keep running our program, and then the operating system will kill the program. So let's take a look at some types of exceptions and interrupts. So you can have synchronous and asynchronous exceptions and interrupts. So synchronous ones are ones that happen at the same instruction all the time. Asynchronous ones are caused by external devices and happen at different times. So if you have an instruction that's always causing a divide by 0, that would be a synchronous exception. You can have user-requested versus coerced exceptions and interrupts. So coerced ones are coming from the hardware, and user-requested ones are when the user requests something. So for example, interacting with the operating system. Some interrupts are user-maskable, and a lot of them aren't. So if it's user-maskable, that means that the user can turn it off, so that the hardware and the processor don't pay attention to that event. There's also a distinction between within and between instructions. So this is whether the event prevents the current instruction from completing, or it prevents instructions after the current one from completing. And then we've got this big one here, which is resume versus terminate. That is, can we handle the event, or do we have to kill the program? So some things the operating system or the program can fix up, but other ones just mean the program has crashed and it needs to be killed by the operating system. So let's take a look at a whole bunch of exceptions here. So here are a bunch of different exceptions: I/O devices, going into the operating system, breakpoints, page faults, etc. Let's take a look at a few of them. So here's integer overflow and floating point overflow. These are exceptions that happen in the ALU when you're doing math or the floating point unit. And if you look at these are going to be synchronous, that is, they're always going to happen at the same instruction. They're coerced, that is, the user doesn't ask for them, they just happen because you're using the hardware. The user generally can turn them off. So if the user doesn't care about overflow, the program can say, don't tell me when the overflows happen. And you can resume from these. So if you have an overflow, the operating system or the program can go and figure out where the overflow happened and try and clean it up. Here's another one. This is a memory protection violation. And this is non-maskable. So this means that the program can't turn this off. And the reason the program can't turn it off is because this is a terminate type of exception. If you go and access protected memory that you're not allowed to, that means there's something wrong with your program and you're going to crash. This is what's known as a seg fault or a segmentation fault. That is, you're trying to access memory that's not in your own segmentation. So let's talk about exceptions and MIPS. What can happen in which stage of the pipeline? So here's instruction fetch. So instruction fetch, we can have a page fault. That is, you're trying to load instructions from a part of memory that's from data that's not been loaded into memory. And on a page fault, the operating system is going to have to go fetch that data from the hard disk and load it into memory. You can also have a memory protection violation if you're trying to run code that's not your own. In instruction decode, you can have an undefined or illegal opcode. That is, you might have an invalid instruction. And this happens if your program's corrupted or if your program has been compiled for a newer processor that has newer instructions. In the execute stage, well, you're doing math operations, so you could have a divide by zero or an overflow. We'll get to the memory stage in a minute. And in the write-back stage, you can't have any exceptions. And that's because you're not doing any computations. The write-back stage is just putting the data back into the register file, and if there was something wrong with the instruction, you would have had an undefined or illegal opcode earlier on in the pipeline. So, for the memory stage, which of the following exceptions cannot occur? Well, divide by zero is the one. So we can have page faults and misaligned memory access and protection violations if we have an address which is in the wrong place in the data memory. But there's no division going on in the memory stage, so we can't have a divide by zero exception. So let's take a look at some example exceptions. So here I've got 3 instructions I'm going to run, and I go ahead and start running through my pipeline, and at this point I get an overflow exception in the ALU for my first instruction, which is an add instruction. So the next instruction needs to jump to the operating system to clean this up. So now I'm going to go and load code which comes from the operating system, and I'm going to start running the code in the operating system to fix this up. However, once that happens, I've still got these other instructions that are sitting in my pipeline. So these can't continue because I have this exception I have to handle. So I need to go kill all of the instructions after the exception, just as we did when we mispredicted a branch. Now when this is all done, the operating system is going to go back and it's going to start rerunning the add instruction once it's fixed the exception. We can also have tricky things happening in the pipeline with exceptions. We can have multiple exceptions at once. So here's the same code, but now imagine we have a page fault in the load word instruction when we get to access the memory. That is, it's trying to access data that isn't in memory yet. And at the same time, the add instruction generates an overflow exception in the execute stage. So now we have 2 exceptions generated by 2 different instructions in the same cycle. So load word has an exception in the mem, and add has an instruction in the execute stage. So how do we handle this? Well, what we should do is we should handle the first one first. So we should handle the load word instruction and take care of that. And so that means we're going to have to kill the instructions after that. We're going to have to go into the operating system, load the page, and then re-execute load word. Once we've re-executed load word, we're not going to have an exception since the operating system fixed up the page fault. Then we can go on and re-execute add, and now we'll get the overflow exception, but we don't have any others, so we can handle that one by itself. Can even make this more complicated. So say the load word instruction has the same page fault exception, but now say the add one has an illegal opcode exception in cycle 2. What's the right way to handle this? Well, we have the load word, which is the first instruction, having an exception in cycle 4, and add, which is the second instruction, is having an exception before it in cycle 2. So how do we handle both of them? If we're precise, that is, if we have precise exceptions, we're going to have to go in and realize that the load word instruction ran first, so we'll have to handle its exception first. If we have imprecise exceptions, then we're going to handle whichever one comes first in time. So then we do the add instruction first since its exception happens in cycle 2. Remember, this is another one of these cases where the promises the ISA makes about being sequential and atomic get broken because what we're doing in the pipeline is neither sequential nor atomic. So, to summarize exceptions, these are really tricky. It's extremely hard to design these right in a processor. We saw 2 cases where they're tricky to do in a simple pipeline. Imagine trying to get this right when you have a 17-stage pipeline and 50 instructions that are all executing at the same time. So very tricky. But they're also very important. If you don't do exceptions right, it's very hard to debug your code. It's hard to know that your operating system is running correctly. So it's critical to get this right. And we saw a little hint of some of the trade-offs here. So we saw that we could do these imprecise exceptions, which are easier to do, and sometimes we need precise exceptions, and sometimes you can do that by writing the software differently when you need precise exceptions. So a question about user-maskable exceptions. Why is the undefined instruction not user-maskable? Well, if we have an undefined instruction, it indicates an invalid program. So programs should never have invalid instructions. If one is found, it means something's corrupted or the program can't run on this processor. In that case, there's no point in running the program since we can't get the right results. So which one of the following is not a way in which pipelining makes exceptions trickier? Well, exceptions can occur in math operations. This doesn't have anything to do with the pipelining. This is you can have an overflow or divide by 0 when you have an ALU. However, having multiple exceptions at the same time and having multiple exceptions in the pipeline are both the result of the pipelining.